А мы бы хотели, чтобы и студенты просто пока.
Окей.
Ну ладно, удачи.
Хорошо. Сейчас видим. Окей. Let's start then. It will be, I guess, I don't know what lecture it is, but let's denote it like lecture 1. And as I said, I'm Azamat Devonaev. Here is my email. You can ask any question you want. I will upload these notes basically in your, I don't know, I will give it to Zara, and Zara will show you what we need to do. So what I'm going to do basically today, we are going to discuss some econometrics. So basically, I want to discuss with you what is econometrics, just to motivate it, because it's kind of introductory lecture. And we will discuss what is the model. And so, yeah, let's write it this way. First of all, like, what is econometrics and why you need it? The second question would be, what is the model? And after explaining this, I will show you what the causality is. But we will go to this into details. It's just an outline. It is an outline. Outline. And after this, I want to discuss with you the very famous tools of econometrics. It's basically regression. And specifically, we will discuss the linear case. And we will see also what kind of assumptions we need to model causality. And then after this, we'll talk basically about the data and how you estimate your model. Estimation of the model. But what we are going to see in this estimation is the particular case, which is called ordinary least squares. And after deriving these estimates, we will examine some properties of the. Yes. We will see. Feel free to interrupt me in any moment that you want. It's just like, if you have any questions, if you want to clarify something, if I'm writing something that is that you don't see well, just tell me. We can fix it, I hope. So, okay, the properties of the estimates. What is basically it means? It's the property of the consistency and asymptotic normality. And then when the time, I think mostly we will cover like consistency, not asymptotic normality in this lecture, because we have not that much time. I will basically do the consistency, and then if time allows, we will do interpretation. Interpretation of the model. So, okay. Is there any questions like so far? Like everything is so far so good? I mean, if you want to clarify something about the outline, what we are going to discuss, just tell me.
Not yet.
No, everything is clear.
Great, great, great. Yeah. So basically, what I want to start with is the first question that we outlined: what is econometrics? To answer to this question, basically, it is the statistics applied to economics. I'm not a econometrician, so don't, the econometrician maybe might kill me for these kind of statements, but basically what it means, it's you apply like statistical methods, application of statistical models to economic problems. I just want to give you some like historical remarks, like history. Basically, econometric, the first econometric society was in 1930s in US by, I think it was Irving Fisher. I don't know what kind of Fisher it was, but it was one guy named Fisher, I'm sure. And you can see it. And this guy basically, these guys, they created this econometric society, American. Where they basically started to measure some economic models. Because, for example, I don't know if you have seen the macroeconomic models, like, for example, you have this Keynesian cross model, like in the ISLM model, for example, what you have is the IS curve, which is basically derived from the Keynesian cross. And in the Keynesian cross, you have basically the marginal propensity to consume in the economy. Basically, it means that what share of your income you use it for consumption. So it's like some kind of fixed parameter that basically whatever income that you have, you basically, I don't know, 60% of 80% or like 40% you use for buying food or whatever. And this kind of thing in their model, it was like a parameter. And in order to reveal it, you need some econometric tools, statistical tools to estimate those kind of parameters. So basically, it was because of these kind of things, the econometric like statistics applied to economic problems was done. So far, any questions? I mean, if it's okay, let me move.
It's okay.
Is what is the model? And here I would like to ask you actually, what do you think is the model? So if anyone wants to answer this kind of question, please. Just give me some like, answer. I'm sure that we will get something meaningful out of it. I mean, it's. Does anyone have any understanding what is the model? Okay. If not, I mean, the model is basically the version of the reality. What I mean by this, that it is the version of the reality. Reality is like something that we don't really understand. Like it's like something that is unknown to us. And by modeling the reality, we want to understand like something about what's going on around us. And the fundamental feature of the model is basically is that all models are wrong. Because it's the model is something like artificial that is basically like built to understand reality. First, think about, for example, the classical mechanics of the Newton. Newton basically was the guy who was asking questions why stuff falls. Is there any question? Excuse me, I don't. I guess someone has a question and he wants to ask, but is there any question, guys?
No, everything is clear.
Okay, so basically, like think about the classical mechanics of Newton. The guy was saying that you have the gravitational forces. That's why, like, apple falls, I walk on the ground. Everything is like falls to the ground. He was modeling it by the gravitational forces. I mean, he cooked up some like laws, and it basically explained a lot of stuff around our world until 20th century, when, like, for example, Einstein came and said that, okay, Newton's model doesn't apply to many other stuff in reality. So basically what he did, he actually explained the reality much better with its own version of the reality, the Einstein's model of reality, which encompasses also the Newtonian classical mechanics. Like, I mean, this is like the fundamental feature of the modeling. All models are basically some version of the reality, and it's wrong. It's true until it will be proven that it is wrong. Because, for example, Newton was right until the beginning of 20th century, but then Einstein came and changed it. So we will see after, I don't know, maybe some 10 years or 100 years, another guy coming and saying that, okay, Einstein's model doesn't work now. So we need to build something new, because yeah, it's something that doesn't take reality better, because all the models are approximations, and when you get better approximation, is basically it's a new model. So this is it. Like, so basically this is what is the model. Do you understand what is the model now?
Yes.
Great. If you understand this, then I'm sure that you will understand the rest of the course very easily. So let's ask the third question that I asked. It is about the causality. Like, let me first, show you some picture in the picture, like what is the model. It's basically, as I was telling you, it is just think about like reality as a realization of some model generating machine, like a data generating machine. Basically, what we see that around us, like you are, for example, I don't know, right now in the university, or the state of yourself, like in some dimension. For example, if I take our wages, for example, I have different wage, you have different wage, and the theory would be that wages are actually determined by something about, I don't know, about your education, about your, I don't know, hopefully not gender, or I don't know, about race, something like this. So basically, what we observe is the data in reality, and you have behind this thing that is observable, you can see it. People in the reality, they have some data, they have some thing that you can measure, and you say that this data, it is generated by some unknown and unobservable data generator. It can be equivalently said to be like a nature. It basically, I mean, what is like this? It's this thing that generates this data, and since you do not absorb this one, because I mean, if we did absorb this model data generator, we wouldn't need any models. Because if you know, it's like knowing how world works. It's like already knowing how reality really works. You don't need any models. Like you don't need the classical mechanics of Newton or like the theory of Einstein that how reality works. What we see actually is the reality, the observable stuff. We see this, and here basically we want to work backward. We basically from the data, from the reality, from observables, we employ econometrics. We employ econometrics to study from the data this unknown theory. And the way that you employ econometrics is by building models. Is by building. So what it means basically is that the model would be some kind of a function where you put some like input, like I don't know, some observable characteristics, and you get an output. I don't know. Also like observable, but for example, it can be like wage or something else. Do you guys understand what I'm talking about?
Yes, we understand.
Great. Just tell me if something is not okay. So this is basically what is the model and what the econometrics is about, like the big picture, basically. So what I want to discuss next is causality in our outline. Now, do you guys know any difference between causality and correlation?
Yes. Correlation is a relationship between the variables, but causality is that logical relation. For example, we can have correlation, but in the same time, we can have no causality.
Exactly. I mean, this is the way you understand it. I mean, causality is basically like a real causal relationship between some variables. Correlation is basically it's the statistical, not logical. I mean, it's just statistical relationship between some variables, random variables that doesn't have any meaning. So in this sense, I mean, what we want to model, if we want to model something that, like saying that wage depends on education or something else, it's always we are interested in the determination of the wage via the causal link from the explanatory variables. Like, and here you cannot just, use for explanation of the wage, the temperature in the Brazil, or I don't know, like how many like wage in Armenia, for example. You cannot determine it by what's going on in Mars, or I don't know, something completely like unrelated. And here it is related fundamentally to economic theory because if you want to explain like wage with the something that is going on Mars, then I mean you have to be very clear. I mean you have to be very clear that there is like a economic link. There is a link that something going on Mars, basically it affects the wages in Armenia. So I mean it is very hard to do so. So basically that's why you don't see any sensible models encompassing this kind of variables. So that's why you have to build your models like causal models. Causal models always rely on the economic theory and the some like assumptions of the regressions to make sense. So yeah, I mean, so you understand, right, that you need to be very careful when you try to capture some causal relationship between stuff, because there should be economic theory behind it, because otherwise you will encompass some like nonsense, like no some statistical relationship which doesn't make any sense. No questions? Okay, the next, another property of the causality relies on the concept of potential outcomes. It is super important concept, and what I'm going to do right now is basically to explain it to you. So suppose, take one person, just take one person, and gather some data about that person. For example, you have like wage for this person J, which is measured, in dollars. You can see the education of this person J, which is measured in the, I don't know, schooling years. I don't know, some other, you tell me, can you give me any factor that can explain wage?
Age. Wait.
Age, exactly. Age for this person J, which is measured in years, right? So I don't know, let's take the I don't know, military service. It's the classical actually. Military for this person J, which is measured in the whether it's served or not served. It's a dummy variable, basically. So what you can see, it's like this one is age can be some real number. No, some integer. No, not integer, actually it's some natural number. Education is also, some natural number. Well, this one, the wage can be, and it can be a real number. In military, it can take, either one if served, 0 if not served. But let's think about this military thing. When you gather data for this person J, you see one realization, right? You see that this guy served or this guy did not serve. So basically, if you wanted to capture causal relationship between military service and the wage, you should compare like apples with apples, not apples with oranges. You should compare like this guy, I mean, you see that he went to the service or not. What you can do is basically, I mean, you need to think about the alternative reality when this guy did not serve and he stays the same. And then what would be his wage? And what you could do basically, I mean, if you had these two potential outcomes, when the guy served, the same guy, and the same guy did not serve, and you could see the difference between wages, you could take just simply the difference. I mean, you just subtract it. This is like a true causal relationship. Let me write it down. This is basically, I mean, the wage when I mean all the education of J is I don't know, some I mean it's keep just basically constant, age and military equal to 1 minus wage age military it is causal difference in wage due to military service. I mean, don't forget about the theory that, I mean, of course, military service might be really related to the wage because, I don't know, the person that goes through the military, for example, they might be, I don't know, maybe they get better in the problem solvings or they get even worse. So, I mean, there is some like theoretical link between wages and military. And this is why you build this kind of, this is why you think that this thing matters, and you can say that there is some causal relationship or not. So is there any question so far about the potential outcomes? So you see, right? I mean, why you need the causal.
Yes, we understand.
Great. So let me move next. If you remember in the outline, we had the regression tools. Okay, so until when I'm going to teach it, it will be 12:30, right?
In our time, it might be.
Oh, okay. So it's 1 hour and 30 minutes, right?
Yes.
Great. Okay, I have to manage time because, I mean, yeah, we have a lot of stuff to do, but I don't want to miss and I don't want to go fast in the end. So regression tools. What you really have in econometric is basically, I mean, you have the famous, I mean, the regression. The regressions can be like the linear or non-linear, but in this class, we are going to be interested particularly on the linear regression. And what you can see is basically, I mean, it's about some relationship between the captures the relationship between random variables. I just immediately tell you that, okay, there are some prerequisites that I will use right now. Like, I mean, you should very well know, not, I mean, very well, but I mean, it's assumed that you know prerequisites. I hope it's right. You know, like some basic like probability and statistic. Specifically, like the properties of, okay, wait, like, you know, random variables, you know, expectation, you know, conditional expectation. And you know, properties of the conditional expectation. And also, I mean, apart, this is, I think, oh, okay, you need to know also, I mean, the law of large numbers, central limit theorem, and the convergence of random objects, random variables. Then you need linear algebra and a bit of like optimization calculus. Okay, that's it. So basically, I mean, this is something like you have to know, because I'm going to use like extensively these kind of things, and I hope you don't have any problems with this. Basically, the regression is written in the following way. You have like some y, to say that depends on x plus some unknown, unobservable, unvariable. So some terminology, y is usually called a dependent variable. In this case, I mean, it's a scalar. It's basically the random variable. It's not a random vector. Random vector, its size basically is like 1 by 1, right? And then you say that you have here independent variables. And this is a random vector. Its size is basically, I mean, x is basically a column vector with the coordinate, I don't know, like the first coordinate, the second coordinate, the kth coordinate. So what you have is basically its size is basically, I mean, 1 plus dimension, 1 plus k. No, it's k by 1. It's k by 1. Because you have k objects inside this vector. It's a column vector. It has k rows and 1 row, right? And in my case, all the like vectors are column vectors. Notation. Vectors are columns. So basically, what you have here is also a beta node, and it is beta 1 until beta k. And its size is also k by 1. Does anyone tell me like what this X transpose beta 0 is in terms of the size? Just see, like X transpose beta node is basically what we have. X, I denoted, I mean X is this, right? So what you do is basically you transpose it. Right? And then you put just this beta. I mean, it's a column vector, so it's written this way. I mean, it doesn't have any transpose. Basically, I mean, what you have is beta node 1, beta node 2, and beta node k. So what happens when you have this kind of multiplication is what you get. I mean, dimension of this one is like dimension of this is 1 by dimension 1 by k, and this one is k by 1, right? So what you get is basically something. I mean, it's basic matrix multiplications, like 1 by 1 object. So it's basically like some scalar, right? It's some number. I mean, which makes perfect sense, because I mean, what you have in this object this one is scalar, this one is scalar, this one is scalar, and these ones are like vectors, and this one is causing the big problem. This because x transpose is a vector and beta node is also a vector, but since it's the product of these vectors, what it actually gives us, it gives us this this scalar. So basically these two things, it also becomes scalar. So there is no problem in consistency in the matrix form, right? This is it. This is basically it. And what we can say right now, is there so far any questions?
No.
Yeah, if anything is not clear, please tell me, because I mean, feel free. So what we are going to do right now, let's call this one like equation 1. This one. And what we are going to do is impose some assumptions. We need these assumptions just because we want to capture the causal relationship between variable x's and y. To capture the causal relationship between y and x's. It's not a transpose. It's just, I don't know how you x's, right? So the first assumption, I don't know, like let it be A1. I want the expectations of the model error to be 0. I mean, this assumption is not a really like strong assumption. It's not restrictive. It is not restrictive. Does anyone know why? Does anyone know why the expectations of the model error is 0? It's not a bad assumption. Remember the some probability, some.
There are nobody now.
Okay, I mean, you do not impose, I mean, it's not a restrictive assumption because you always have this alpha node, right? The existence of the intercept, allows to normalize expectation of model error to zero. Because if it's not zero, if it's not zero, but if it's any constant, it's a mean, right? Expectation. If it's not zero, you can always just add up an intercept. I mean, whenever you add just an intercept, it's like a level up or level down the line, and there is no problem. You can subtract or you can add. There is no problem. It's not a restrictive assumption in this sense. But what is a restrictive assumption is the second one. Now we impose like the assumption of the mean independence. Mean independence, or you can exogeneity of model errors U with respect to regressors, i.e. x's. So what you see basically here is like now we are putting more like some assumptions that this is not necessarily like true. It's quite strange to say that model errors are like mean independent from the regressors. Like what it actually looks like, it's we are saying this in the probabilistic term. I mean, it's basically saying that expectation of the model error conditional on the regressors is zero. I mean, this is like something that basically you say that it's not about saying that it is not. I mean, it is not about that random variable u and x is independent. It's not about this. It's about it's weaker. I mean, this thing is weaker. This one is stronger. Because independence, I mean, this independence implies this. But this one does not imply independence. You see, right? That it is weaker, but still, I mean, it is assumption. It is an assumption that may not be true, and I mean, it is relatively quite strong assumption that we are imposing to the model. For example, the expectation of u being zero, it was, I mean, okay, you can just level up, level down your model, it's okay. But this thing is like very artificial thing that we are imposing just to have a causality. And the reason why we do it, because if you don't impose exogeneity or mean independence, or how it's called else, I mean, I don't know, it's like, it's called, I think, orthogonality of means, something, okay, zero mean independence, basically. I mean, if you don't impose this, you don't have a causal interpretation. Let me say causal relationship. Because remember that you had this model. Again, I will write it down just to make it clear. I mean, what you have is this thing, right? And what you're going to say is basically, I mean, what is the best predictor of the y? Y is random. What we can say is basically all is about its expectation. It's expectation, but since we have like a theory and we have like more information, we can say that what is the expectation of y given x, right? And that will be like what? I mean, it will be just this whole term, like this thing will be conditional on x. I'm just rewriting it, right? And what you can see that by properties of the conditional expectation, what you have here is basically, I mean, when you give like this x, this thing is known, right? Since this thing is known, it can be like taken out from the expectation. So basically what you have is like alpha 0 x prime beta z naught plus, but we don't know anything about this one because this thing, we don't know like what it is. It might not be, it might be some function of x, but that would be like a real trouble. Because if it is a function of x, I mean, then you don't, if you move around, you see, like you will move around all the time when you change like x's, you have like, since you don't observe this u, it will move around and will cause some troubles on your explanation of the y. So basically, that's why you impose this condition that this thing is 0. I mean, this is your assumption. Your assumption. It might not be true. Just I'm saying this. And as an econometrician, the art of doing all this stuff is just to make sure that when you build a model, this condition holds. Let me write it down. As an econometrician, the art or the science is to make sure that in your model, this one is true. And it's not easy. You will see that like there is plenty of issues like endogeneity, you have these instrumental variables, there is a whole mess is going on because of this assumption that it's not really, I mean, you cannot find these things in the real world. And the problem, of course, if you can just sense, because I was telling about this causality thing, and actually the problem that is coming is actually from this causality. You see this potential outcomes. I mean, because you don't observe one the alternative realization of one person, I mean, it creates a whole plenty of problems. And since you don't see it, now the art is you have what you have. I mean, you have like the real world, you have just only one outcome. You have to do your best to get some meaningful relationships. And that's why we need like science and smart guys like you. So this is basically it. So, I mean, you understand, right? Like two assumptions. I did only two assumptions. Like, and the first one was not, I mean, it's not a restrictive one. A1, it's not restrictive. I mean, it's very okay. It's not even an assumption. I mean, it's just like a mathematical triviality. And this one is a strong assumption a bit. Since it's not independent, just to make sure that it's not about independence of the U and X. It's about the conditional independent, like the first moment restriction. It's about the mean of the U with respect to X. And of course, there is also the A0. I mean, I forgot this about this one. A0, let's see, that betas and alphas, they enter the Y is linear. Y as a function of X is linear. Because I mean, what we have, it's a linear model, right? Because it's not, if it's not a non-linear, if it is non-linear, then there will be plenty other issues. So, I mean, we are not studying this stuff because, I mean, OLS about the linear stuff. When you do the probit logic things, then there you will see some maximum likelihood and other estimations. And there you will touch about the non-linearity and stuff like this. But A0, I mean, no worries. I mean, it's not something that, ignore it for now. Let me write this way. Okay, so far, any questions? I mean, just, it's clear?
Yes, it's clear. There's no questions.
Great, great. Actually, I want to just tell you this. Actually, A2, assumption 2, implies assumption 1. It's even redundant. I mean, the way that we said that the expectation of U is 0, it's, I mean, redundant. Because what you have here is expectation of U given X 0. Suppose it's true. Then, by the properties of conditional expectation, expectation of U given X is equal to expectation of the expectation of U given X given X. If you know law of iterated expectations, let me write it this way. Law of iterated expectations. I hope, I mean, if you don't remember, just go back to your probability and the statistics class. It is there. I mean, I'm sure that this thing is one of the most important properties of the conditional expectations. So basically, you can write it this way. Okay. Let me see. This thing. Oh, okay. Okay. No. Sorry. I wanted to show you something that, but it seems I got confused. Really, I'm sorry. No. Forget about this implication. No. This implication is not from here. This implication actually is from it's about the conditional expectation. Now I see. Okay. No. A2 does not imply the. I1. It's. I have to think about it. I mean, I'm thinking about it right now. It makes sense, but okay, wait, that's strange. Okay, no, okay, no, Okay, it doesn't matter. I mean, we have these two assumptions. That's it. It's all right. So I mean, now let's get to the data. Because you remember, we have the model, but we don't, we need to estimate it. I mean, you see, right? So what we are going to do is basically recover our, like, to estimate the theoretical model. Let me write it this way. Theoretical model, again. This is the theoretical model. And next, we are going to estimate. Okay, I think it's 2 now. It's 1 actually. We are going to estimate 1. Do you have any idea how?
Maybe no,
How?
we don't know.
Okay, you use, I mean, what? Would you use the data? You use the data. By the data. Just to tell you some brief explanation types of data, I will give you some explanations types of data, because then you will see, like, for example, panel models and stuff like this. So I just will give you some brief cases of the data. Data is basically, I mean, you take it from the outside, right? I mean, like you see the person with, I'm male, you are female, or I don't know. I was born in Tajikistan. You were born in the Armenia. It's basically all the realization of the nature. Nature basically draws, and you are born there. I mean, you are assigned somewhere. So we can collect this kind of data. We have like some random variables, like I don't know. So basically, it's collected. What you have, like 3 types of data. You basically have 3 types of data. First is cross-section. Cross-sectional data. Second, it is time series. Third, it is panel data. Do you guys know any, like, have any idea about what kind of, okay, there is no problem. Okay, the first one. I will give you some brief explanation. Cross-section is basically, you have individual data on some random variables. So what you can do mathematically is basically, it's like just you have like some set denoted by, I don't know, J. So basically, it's this kind of collection. You see, right? J denotes like individual, and you have n observations on y, x1, x2, ... to xk. This is the structure of the cross section. I mean, like if you see it like a table, then it's like this. It's like this. You see, right? It's basically this. I mean, do you guys want me to show you the time series or panel data? I mean, I can. Okay, let me show you briefly, like the sort of like the definition, but I will not draw because drawing takes too much time. In the time series, you have one individual data on some random variables across time. So what it means basically, you have like, I don't know, for example, just think about Apple, the company, like its profit, for example, SY, it's one observation. And you see that it has many characteristics, firm characteristics, access for this one Apple company. So you have one observation, but you can see that the performance of the Apple is like from, I don't know, 1990 to 2022. So you have basically like 32 observations of in years. Basically, it can be written like this. Oh, sorry. I mixed up T's with J's. Capital T. So you basically have T capital periods, and you have basically observations across time, but one individual. Basically, either Apple, Microsoft, or I don't know, me, you, whatever. The third is the panel data. So here what you have, it's basically, you have observations across both time and individuals. Right? It's like now you don't have like Apple across time period, but you have Apple, Microsoft, Google, I don't know, something else. So you basically have different observation across time periods. This is a panel. It's a richer, I would say, structure of the data. You have basically observations, and also you see it on the time horizon. So what you can write it, it's basically it's like this. You basically have J, T, X1, J, T, X2, J, T, x k j t. So now, I mean, here what you can do is basically like you have j and t greater or equal to 1, and here it's like n and t. Right? No problems. Is there any questions? So,
Okay, it's clear.
okay. So now what you do is we restrict ourselves to cross section. The panel and time series, I mean, it was just for you to know, because after my seminars, there will be, I guess, the panel data. Don't freak out. I mean, it's you know the structure of the data. I mean, so we restrict ourselves to cross section. It's not as rich as panel data. So now recall our model. Okay, it was like this, right? And the goal is to estimate it now by the data. The goal, estimate one by the data. And the idea is basically is the data that is basically, I mean, it is like you have this collection of yj's, right? Because it's cross section. This x is a vector. You have basically this kind of data, right? So the idea is minimize the sum of squared errors So what you can do is basically write like this. And then the sum of squares is basically like this. Do you agree that it's like this? Is there? Oh wait, I forgot the summation, right? I mean, it's silly. Do you agree that it's? Do you see the link? No problems, I hope. And I mean, so you write it this way. The only thing is left is like you just minimize it. Minimize it. Can you tell me with respect to what?
We didn't hear the question. Sorry.
You didn't get what? Можете спросить на русском, если хотите, как угодно, комфортно, как бы не, ну, типа, можно спросить все, что, как вам захочется. Что непонятно именно? Если непонятно, ну, второе, первое, где? Вот.
Нет, все нормально, спасибо.
Окей. Просто в чем заключается идея, да? Мы минимизируем квадрат ошибок, да. Вы лучше меня знаете. Sum of squared errors, квадрат ошибок. Потому что, ну, как бы, просто квадраты ошибок, там, типа, будет плюс и минус, там не все так очевидно. Поэтому самый лучший вариант – это наименьший квадрат, называется метод наименьших квадратов, типа OLS. Ordinary least squares. So, basically, что мы делаем? Мы, как бы, записали… Let me turn to English because I don't want to confuse myself too, because I mean I'm really not good with this concepts in Russian. Why what do you have? I mean, what is known here? What is known? Just think about, like, you collected the data on what? Here you collected here the data. These things are known. So that's why, I mean, you have here, it's the thing that is known is like y and x, right? This thing is already known. What is unknown is alpha and beta, because the goal is, like, I mean, what we know really in the real world, I mean, we know y's and x's, but we don't know how y and x is related. We see that we say that by the theory, it's the linear relationship, but we don't know, I mean, you have like plenty class of linear relationships. You can have like beta equal to million, or you can have beta equal to 0. So what we are going to do is we're sort of like fitting the absorbed data. We are taking the best possible alpha and betas to minimize the errors. So that's why you minimize with respect to alpha and beta, and alpha and beta will be basically like arg minimum this one's the alpha least squares, I mean beta, it's the best one basically. When you already minimized your function, you get this alpha and betas that are very special because they minimize. It's the unique solution for this minimization problem. So do you guys, I mean, have any idea how to minimize the function? Let me write down this. This maximization program is like 3. How do you perform this thing? How do you minimize function?
1 minute, please. We are trying to find English word for that.
What?
We are trying to find the English word for that. We know the answer, maybe. I think.
No.
Может найти производную для функции?
Отлично, супер. Производная, первая производная. Просто берем первое производное и приравняем к нулю. У нас как бы тут квадратичная функция, понимаете, да? есть second order condition satisfied, поэтому там есть unique minimum. Поэтому проблема тут довольно понятная, потому что это есть вообще? Ну, типа, то есть, ну, как бы, в общем смысле, тут как бы задача вот такая. И тут всегда, потому что, как бы, ну, вот представь себе u squared, правильно? И вы минимизируете, и, естественно, здесь вот находится какой-то максимум, или вот здесь, я не знаю, какой-нибудь, короче, там вот нужно выбрать такой альфа и бета, который вот минимизирует эту штуку. И там производная, как вы сказали, будет равно нулю. So let's take this first order condition. So what we are going to write here basically is this. Так, первое это мы будем брать по альфа, да? У нас там две. We have two parameters, like we have alpha parameter and beta parameter. Пока понятно?
Да, это понятно пока.
Это как бы скаляр, scalar. И that's why it will be, I mean, the way that you minimize, let me see how you minimize this thing. Let me see the function. So function is like this. So how you, I mean, take the derivative is you use the chain rule, right? Because it's a complex function. Not complex, it's composite function. I don't know how you call it, like, because it has this, you need to use the chain rule, right? Сложная функция. That's why we basically have two summation, and here you have yj minus alpha minus xc transpose beta, and what you have here is also is like this inner derivative with respect to alpha, which is -1. Do you agree? Equal to 0, right?
Yes.
And the second one is a bit complicated, because now you are taking the scalar derivative of the scalar with respect to the vector. You see, right? The x is a vector. And here I will rely on your knowledge of the linear algebra. Basically, what you have is, what you get is, it's again 2 and J1, you get this yj minus alpha minus x transpose beta, but you get also like, oh, sorry, I'm very sorry. I'm very sorry because I made a very silly mistake. It's not x, of course, it's beta, right? Because I mean, we are taking, I mean, we are minimizing with respect to the alphas and betas. But I mean, it's still vector, you know, right? The beta is a vector because it has a lot of components. And what you do is, we got the first derivative from the function, and then we apply the chain rule. And here you see that x transpose beta, derivative of x transpose beta with respect to beta is x without transpose. This is like a simple, I mean, it is the linear algebra, I mean, derivatives of the like vectors and matrices. It's not that hard. So you can see that you already have like a system of equations. Can you tell me like how many equations you have here in the system? How many equations and how many unknowns you have. Let me denote the system by 4. Just be like, I mean, slowly, like, what is the dimension of?
I'm trying to find out answer.
Yeah. So let me remind you. Recall. Just look at this. Like, alpha is a scalar, right?
Yes.
It's 1 by 1. What is the beta?
The vector.
It's a vector. It has 1 coordinate.
Yes.
Until when? Until
1.
no. It has k coordinate, right? Because you remember. Let's see in the beginning when I was defining stuff. Where I defined it. Here, you see?
Yes.
K by 1 and k by 1. Because the dimension matches. I mean, of course, for all x, we have its own beta. So just think about it. Like, you have alpha here, scalar, and you have beta, which is vector. So which means that you have k derivatives. So in the sum, in total, you have how many equations and how many unknowns?
2 equations.
How many?
2 equations.
No, because you are forgetting that this thing is a vector. So I mean, of course, I'm writing it in the notation that I mean, don't forget that it's a vector.
1.
It's k plus 1 equation and k plus 1 unknowns. I mean, you can see, right? Beta is a vector, right? So it's k plus 1 equations and k plus 1 unknowns. Do you guys, does it remind you something? Like, I mean, it's a good news, right? Because it is the system of equation that has a unique solution. Because you have k plus 1 equation and k plus 1 unknown. Think about like 2 equations and 2 unknowns. It has a solution. If you had, like, for example, 2 equations and 3 unknowns, you would have like infinitely many equations. You wouldn't have any identification. But if you have, for example, 2 equations and 1 unknown, it's over-identified. I mean, it's a very hard case. There is no solution either, or there is one solution, but I mean, it's a very special case. So here, basically, you are guaranteed to have a solution because you have k plus 1 equation and k plus 1 unknowns, equations and k plus 1 unknowns. So basically, 4 can be rewritten. I mean, you see, you have these 2's minus 1's and stuff like this. We can get rid of it, right? Because you can always like divide both sides by 2. I mean, you can get rid of this, and this, right? So what we can do, 4 can be rewritten this way. So, but let me show you, like, the moment that you equalize it to 0, the 4, just look at 4. The moment that you take this first order condition, these alphas already become specific alphas. I mean, they become like the best alphas and betas. And it's called, actually, like, the name of it is the alpha least squares and beta least squares. You see, right? Because the moment that you equalize this, when you do perform this first order condition and equalize it to zero, the derivatives, these equations, when you find the betas, it's a specific betas. It's not any beta and alpha. It's a very nice alphas and betas. That's why it's a very special thing. So we can write it this way. Okay, I think I'm taking a bit. I will take maybe 5 minutes if it's okay. At 12:45. I mean, is it okay?
Okay, you can finish this part, and then we will finish the lesson.
Yeah. Because I guess I missed a bit time management.
Okay.
So I mean, this is like a nice form. Now what I want to do right now, it is to write it in a more nice form. In nicer form. So for this, denote theta least squares as alpha ls least squares and beta ls. Let it be the vector. We defined it. I mean, we defined it. We just stacked basically like alpha and beta in one vector. It's perfect. Okay. I mean, you don't have any problems, I guess, right? What is the size of it? Can you tell me? Alpha is a scalar. This is the vector. Dimension of k by 1. So what you have basically here, it's 1 plus, you have 1 plus k columns, like rows, and 1 row, right? One plus k rows and 1 column. And also, I want you to denote x tilde this way. You will add 1 and here x. So basically what you have is here is like 1 plus k again, rows and 1 column, right? So now 5 can be written as the sum of x tilde. Now you see I'm using this one. It's from here. X tilde, it's yj minus x tilde now. And here I use theta ls. It is equivalent. I mean, it's really equivalent to 5. You see why? You see, right? I mean, basically, the way that you can write it, it's like this. What you have here is like 1x, and here you have yj minus 1x. I'm just opening it. I don't know, like, I mean, it's there is no need, but I'm opening it. I mean, just to make sure that you understand, right? I mean, it's just the way that you write it. I mean, this thing is just better form. I mean, it's more beautiful.
Okay.
Makes sense, right?
Yes, yes.
So denote it like as 6. Let me take the equivalence form. Now 6 is basically a system. I mean, this thing is a system. I can open the brackets. It will be like this. Right? I mean, you can see, right? I just multiply these things, and then you can, I mean, move around. Oh my God, this is crazy. So now what you have here, basically, I mean, this thing, this is a matrix. You see, right? It's a matrix. Matrix, its size is like, what is the size of X tilde? It's like, you have something that is like column, and it is 1 plus K by 1 multiplied by 1. I mean, it is a row. 1 by 1 plus K. So the product will give you some like big matrix of 1 plus K by 1 plus K. Right? It's just matrix multiplication. So what you can see already here, it's like, you remember this this famous, I guess, I mean, the notation that like B equals to matrix A multiplied by X. It's a system of linear equations in the matrix form. X is theta, LS. A is this matrix, and beta is this scalar. I mean, it's Y is a scalar, and it multiplies this vector. It's just a vector. Vector. So I mean, how would you solve this beta equal to AX? It's easy. I mean, right? You can just do it like this and add here the same thing, right? This thing will give you identity. So basically what you get is X. So basically what you get is, I mean, theta LS. What is it? I mean, just this thing inverse. You see this thing?
Yes.
This thing inverse. Multiplied by the right hand side, I mean.
It's inversion.
This is it.
Inversion, maybe.
What?
Inversion.
Again?
Inversion.
Yeah. We inverted it. I mean, we inverted this thing here, right? So what you get basically, I mean, the whole point was to show that, I mean, you wanted to see this, the formula for alpha LS and beta LS. It's what it is. I mean, it's basically this very beautiful form. I mean, it's like it's closed form solution for this alphas and betas. I mean, it's amazing. It is. You can see already. I mean, this is something that we wanted. Okay, I mean, this is basically like, I mean, the ultimate thing that we wanted to do. I mean, it's basically these estimates that allow us, I mean, to really estimate the model. I don't know if you have any questions, just tell me, because I don't have any time to deal with the consistency, because if you remember, I was in the beginning, I was planning to tell you, let me show you. I wanted to discuss with you also the properties of the estimates, specifically like the consistency. I will not have time to do this because, I mean, we already did a lot, I think. But if you have any questions, just let me know. I can give you any reference or whatever you want.
Maybe not now, but when we will watch the video, if there will be questions, we can mail you.
Okay, let me check just my email. I hope it's written clearly. I feel free. I mean, if you want to ask any questions, just feel free. I'm always, it's Unilu. Let me be very careful, because it might cause some troubles. Okay, this is it. Thank you very much for your attention. I mean, I will try to give this lecture. Do you need this lecture notes? I mean,
What?
do you need this lecture notes? If you don't need, I mean, I will not.
Maybe yes, if it's possible, we need it too. It will
Okay.
help us understand.
Okay. I don't want to take more time. Thank you very much for your attention. Okay. Sorry for this timing, because, I mean, it happens sometimes.
Okay, thank you very much.
Bye.
Thank you very much. Goodbye.
Much.